Thank you so much, Fatima, for the introduction. Let's move on to our first um, person who is going to share presentation. His name is Debjit Ghoshal. He is in BSc Mathematics third year from Ramakrishna Missionary Vidya Mandir, Howrah. His topic for the day is series of reciprocal of prime diverges. So yes, Debajit, over to you.
Good morning, everyone. I am Debjit Ghoshal from Ramakrishna Mission Vidya Mandir. Today, I am presenting on the topic of divergence of series of reciprocal of primes. So, we all know what is a prime number. It is a natural number which is greater than 1 and its factor are 1 and only itself. Okay, so I will not explain that. So, my main focus is if I consider P as the set of all primes, then the series of the reciprocal of primes it should diverge. Okay, I will prove that. Now here is the thing that we will not assume that the set of all primes is infinite. We know we do not know whether the set P is finite or infinite. Without assuming this, we prove this, and if we can prove that the series 1 by P diverges, then as a corollary of it, we can conclude that the set of all primes is infinite. So before going to the main topic, this this is the general harmonic series summation n equals to 1 to infinity 1 by n. We all know that this diverges to infinity, but I will prove it in a different way. Okay. So I consider as the series T, uh, removing the first term of this series. Okay. So I consider T as half plus 1 by 3 plus 1 by 4 plus 1 by 5, etc. I just remove the first term 1. Now I can write this as 1 by 2 plus I can write 1 by 3 as twice 1 by 6. Similarly, I can write 1 by 4 as thrice 1 by 12. I can write 1 by 5 as 4 times 1 by 20, etc. Now I will construct some series from this series. So I construct P1, and what is P1? P1, I take first term from this series half and first term, next term from this segment 1 by 6 and the next term from this segment 1 by 12 and so on. Similarly, I can construct T2 as the remaining term 1 by 6 and next term from this segment this and so on. So here my motivation is I want to construct some series which exhaust them our main series T. Okay. So if you observe here, we construct T1, T2, T3, T4 like this. And if I sum all these series, I mean if T1 plus T2 plus T3 plus T4, what we get is our own actual series T. Right. Is it clear to everyone? Okay. So now I want to calculate what is T1. I mean where this series converges. Okay. So first of all, one thing I have to say that I assume that this series converges because if I don't assume, then I cannot write the P equals to this. Okay. I'm assuming that this series converges. So this is nothing but a subseries of this. So this had to be convergent. Now I want to calculate where T1 converges. Okay. So if I look into the series 1 by 2 plus 1 by 6 plus 1 by 12, I can write it like 1 by 1 plus 2 plus 1 by 2 plus 3. Actually, I'm trying to find the pattern in this series. Now, if I formulate this, I can write as a summation 1, summation k equals to 1 to infinity 1 by k into k plus 1. And by partial fraction decomposition, I can write it like 1 by k minus 1 by k minus 1. Now, if you observe, this is nothing but a telescopic sum. Okay. If I write this series, this is 1 minus half plus again half minus 1 by 3, again plus 1 by 3 minus 1 by 4, and all the terms eliminates. Okay, 1 remains. So this series converges. T1 is nothing but 1. Okay. Now, if you observe, T2, what is T2? T2 is nothing but T1 except the first one, half. See, here is 1 by 6, 1 by 12, 1 by 20. Only this first term is missing here. So we can write that T2 also converges to from. As T1 converges to 1, so T2 is missing this term half. So T2 converges to half. And in similar way, we can show that T3 converges to 1 by 3, T4 converges to 1 by 4. In general, Tn converges to 1 by 1. Okay. So now we had that T equals to sum of all these series T1 plus T2 plus T3. Now what is T1? T1 is nothing but 1. We have that. What is T2? T2 is converges to half. T3 converges to 1 by 3 and so on. So what we get that T equals to 1 plus half plus 1 by 3 and so on. Now see, except this first term, this from this 1 by 2, we have our own series T. We assume it. Now T equals to half plus 1 by 3 plus 1 by 4 plus 1 by 5. So we have T equals to 1 plus itself T. Okay, so we have this equation T equals to 1 plus T. But we assume that T is convergent, but it is only possible when T is divergent. Because if T converges to some finite limit, suppose K, okay, K cannot be equals to its successor. So my original assumption was wrong, but T is convergent. So T has to be divergent. So what was T? T is this series half. So only one term is missing there, one. So if I add 1 to this series, this is nothing but our original series summation n equals to 1 by infinity 1 by 1. So this should also diverge. Okay, is the proof clear to everyone? Actually, here we all prove this series that is divergent in a different way, but here I have tried in a little bit different way. We all prove using the comparison test and such things. Is it clear to everyone? Okay. Now we have proved that this is nothing but it can considered as a subseries of this series. So it may convert or it may diverge. We don't know. Okay. Now I'm assuming this set as set of all primes. Now I'm enumerating this as pi as ith prime. Okay. Now we don't know this set is finite or infinite. Then how this summation I equals to 1 to infinity 1 by pi is defined? We have to define it first. So I am defining it like this that if P is infinite set, then this is well defined, okay, because it is a countable set and we can write this series like this. But the problem is here, suppose P is finite set, okay. Then how series, suppose I have P1, P2, P3 and up to Pk. Then this indices runs up to k, but what after that? I mean, what for I equals to k plus 1, we don't have pk plus 1 primes. So for this case, if we are defining like this that if p is finite, then the remaining terms are 0. Okay. It means it exhausts all the primes and after that, all the terms of the series become 0. So it still be an infinite series. We can consider it as an infinite series. Okay. Now, I will prove that this series diverges by contradiction. So for that, I am assuming that this series, suppose if possible, this series converges. Now, if a series is converges, we all know sequence of partial sum. So its sequence of partial sum also have to be convergent. So suppose I am assuming Sn as the sequence of partial sum, which is summation I equals to 1 from n, 1 to n, 1 by pi. Okay. And this is convergent. I am assuming this. Now, if we recall the Cauchy criterion for convergence of a sequence, we all know that for a given epsilon, there exists n naught belongs to n, such that Sn minus Sm less than epsilon for all mn greater than equals to n naught. Okay. Now, if we apply this Cauchy criteria into this sequence of partial sum, what we get is, let's see, I am taking epsilon as half. Okay. It means for this epsilon, we have an n naught natural number such that I am taking here at s n plus p minus sn less than half for all a greater than equals to n naught and for all p belongs to n. Now, see one thing. What is Cauchy criteria? It says that for all mn greater than n naught, it's here I'm taking a greater than n naught, so n plus p also greater than equals to n naught. So this stays holds. I mean, if n plus p minus sn less than half for all n greater than equals to n naught. And the interesting thing is for all p belongs to n, because for any p natural number, this is also greater than n and n is also greater than n naught. So I can say that s n plus p minus sn is sum less than half. Now let's see what is sn plus p minus sn. Okay. Now what is our sn plus p? I equals to 1 to n plus p. And what is our Sn? Now, if I subtract this, what I get, summation, all the terms from 1 to n are removed. So I get I equals from n plus 1 to n plus p, 1 by pi. This is what we get. And see, this all terms are positive, okay. So I can remove the modulus. So what we get that summation I equals to n plus I from n plus 1 to n plus p, 1 by pi is less than half. And this is for all p belongs to natural number, okay. So this holds for all p. So I can write it like this, that summation I equals to n plus 1 to infinity. Okay. For any big indices if it holds. This means I can write it like this, that summation I equals to 1 plus 1 to infinity 1 by pi less than equals to half. Here I put equals to because it may convert to half. Okay. So what we get that summation I from 1 I equals to n plus 1 to infinity 1 by pi is less than equals to half. Now what we actually did here, if a series is convergent, so I can always count the tail which is less than, whose sum is less than arbitrary positive rational number, arbitrary positive number, sorry. So we get here n plus 1 tail of this series which is less than half. Okay. Now you may ask that why I am choosing epsilon equals to half. So you'll see the importance of choosing epsilon less than 1. Now see, this is a subseries of our main series 1 by pi. And we assume that this series is convergent. This means this also convergent. So we can write it as a term x. Okay. So I am assuming this term summation I equals to n plus 1 to infinity 1 by pi. This I name as x. And see, 0 less than x less than equals to half. less than equals to half we got from here, and it is obviously greater than 0 because all terms are positive. Now consider the geometric series base x plus x square plus x cube. Now see the importance of choosing epsilon as half, because we know that the geometric series converges if the common ratio is less than 1. Okay, so this geometric series have to be convergent. Okay, by what assumption? Now observe carefully that how this series looks like. I mean, how this series defined at. Okay, so what is x? X is 1 by p n plus 1 plus 1 by p n plus 2 plus what is x square? X square is nothing but the whole series square. Now you ask how this square is defined. It means that for any finite sum a plus b whole square, we define it. But for an infinite sum, how this is defined? You can interpret this series square. So this is like, suppose I have 1 by p n plus 1 plus 1 by p n. So I multiply this 1 by p n plus 1 to 1 by p n plus 1. Then this. Similarly, I multiply p plus 2 with all the term of this. I multiply 1 by p plus 3 with all the, and this way we get an infinite series. And that is how the square is defined. And similarly, cube and for any of our, this is defined. Now, whatever the series would be, the common ratio is less than half, less than equals to half, and greater than 0. So, this geometric series have to be convergent. Now, I recall one thing. We all know that fundamental theorem of arithmetic. What it says that any natural number greater than 1 is either prime or can be represented uniquely as product of primes. Now, what is its importance in this scenario? We will see. Now, why I construct the geometric series like this? Okay, what was our initial assumption that this series is conversion? Okay, so I have to reach to a contradiction. Okay, so what I do here, I will show that a subseries of this series is divergent. Okay, so for this that I am constructing the geometric series like this, and why this is important, we will see. My claim is that 1 by k in this series, if and only k has prime factors only from this set, pn plus 1, pn plus 2, and so on. Now, what am I telling here? That suppose assume that our pn plus 1 prime is 2. Okay, pn plus 2 is 5. For some epsilon, we got this. Now, what is x then? X is 1 by 3 plus 1 by 5 plus 1 by x c. 1 3 plus 1 by 7 is 20. Now, what am I claiming that 1 by k or natural number k is in this series. This series in this geometric series. If and only k has prime factors only from this. Now, as k is a natural number, okay, greater than 1, so it has prime factors. So, if it has prime factors, it will be in this series if and only the prime factors are on the tail we chosen. Okay, we chosen pn plus 1 as 3, 5, 7. So, if suppose I am assuming 1 by 75 here. So, what is 1 by 75? It is nothing but 1 by 3 into 5 into 5 prime decomposition. Now, I am telling that this should present in our original geometric series x plus x square plus x cube, because see, all the prime factors of this is in that set. We are considering as tail of the series. Pn plus 1 3, pn plus 2 5. But why? So, see, consider the term x cube. What is x cube? X cube is nothing but 1 by 3 plus 1 by 5 plus 1 by 7 and so on, its whole cube. So see, 1 by 3 plus 1 by 5 is 1 by 7. And multiplying with 1 by 2 plus 1 by 5 plus plus 1 by 7, and again I multiply with the same. Now I am claiming that 1 by 75 presents in this. How? So what is prime decomposition? 1 by 3 into 5 into 5. So I take 1 by 3 from this. So this should multiply 1 by 5. There is a term called 1 by 3 multiplied with 1 by 5. And what we take, we again multiply it from this 1 by 5. So in this series there is a term where 1 by 3 into 1 by 5 into 1 by 5 is present. Okay. So it is clear that 1 by 75 is in this series. Now, in general, from this you can conclude that our natural number reciprocal 1 by k is in this series if and only if k has prime factors from this. Because if k has prime factors beyond this, then we will not be able to produce this term, that term, by multiplying this series like this. Okay, is it clear to everyone this part?
Yes, it is.
Okay. So now I am constructing a natural number m, which is nothing but 1 plus r into p1 p2 dot pn. Now what is this? So see, uh, by Cauchy criteria, we get this series. So what is our x? X is some I equals to n plus 1 to infinity. Now see which primes we are considering here. We are considering Pn plus 1, Pn plus 2, and all primes after Pn plus 2. Okay. Now beyond this there are only finite elements. Okay. P1, P2, that Pn. So here I am constructing a natural number by this prime a equals to 1 plus I into P1 P2 that's Pn. Now I name it as R. So now see, for any I is a natural number here. Okay, for any I, this is a natural number obviously, because one all unnatural, and this is also greater than 1 because m is 1 plus something, and this part is obviously not non-zero, so m has to be greater than 1. Now, by fundamental theorem of arithmetic, you can say that m is a natural number greater than 1, so m has prime factors. Okay. Now see, here m is congruent to 1 mod pi for any I. Okay. Because what I want to say that from P1 to Pn, none of the prime divides m. Okay. Pi doesn't divide m for any I from 1 to n. So, but our theorem, fundamental theorem of arithmetic, we know that m has prime factors, and we also know see that m does not have prime factors from this set p1 to pn. So we can conclude that m has prime factors only from this set. Now, as m has prime factors only from this set, by our previous discussion, we say that 1 by m is the term of the series x, our series x plus x square plus x cube, and this. Now, what is 1 by n? Okay. Now, if I consider this sum is 1 by n over I. Now, 1 by n is nothing but 1 by IR, where R is P1, P2, has Pn. Now, I am running this sum on. Okay. Now, this sum is a subseries of this. Why? Because see, 1 by n is the term of the series. This is true for any I. Okay, now but 1 by n is nothing but 1 plus IR. Now for any I, this holds. For any I, it means for any I, Pi doesn't divide same for any I. So we have that 1 by n is the term of series x plus x square. for any R. So each term of this series, summation I equals to 1 to infinity, is a term of this series. I can consider this as a subseries of this. Now, what is it? Now, you can write as this is a subseries, so this sum is less than equals to our original sum. Now, we can write it because we know that this geometric series is convergent, so any subseries of this series is convergent. And this, where this converges, it either equals to this or less than. So actually what we got that this series is convergent. This is our main thing that we got that summation I equals to 1 to infinity 1 by 1 plus IR is like convergent. Now see, we almost reached to a contradiction because what is 1 by plus 1 by R? We will show that this series cannot be convergent, has to be divergent by comparison test. So what is 1 plus IR is less than equals to, I am just replacing 1 as R. So 1 plus IR is less than equals to R plus IR, which is nothing but R plus 1 into I. Okay. Now if I take reciprocal, then 1 by 1 plus IR is equals to 1 by R plus 1 into R. Okay. Now, if I take the summation, if I consider the series of these two terms, then summation I equals to 1 to infinity 1 by 1 plus IR is greater than equals to, see, this R plus 1 term is constant. Okay, so this just you can remove from inside this summation. So this becomes 1 by R plus 1, summation R equals to 1 to infinity 1 by R. Now, in the past, we have proved that this series diverges. So, any multiple of this series also diverges. So, what we got that this series is bigger than a series which is divergent. It means that this has to be divergent, no? And this contradicts this. We have proved that 1 by 1 plus R is less than infinity summation. This means this series converges. But here, by comparison test, we got that this series is diverges, which contradicts the fact 1. It means there is a problem somewhere. It means that our initial assumption was wrong. Okay. So, what was our initial assumption? Our initial assumption that this series convergent. This was our initial assumption. Okay. But by assuming this, we arrived at contradiction. This means our assumption was wrong. We have proved that the reciprocal of the series of reciprocal of the prime diverges. Okay. Now see here we have not assumed that the set of all number of primes are infinite. There are infinitely many primes. But we have arrived that the series of reciprocal of prime diverges. So the corollary of this, we can say that there are infinitely many primes. Why? Because suppose there are finitely many primes, then this sum is nothing but a finite sum, 1 by p2 plus 1 by p2. And this had to be convergent. But we have arrived that summation I equals to 1 to infinity 1 by pi. Series diverges. So the only set P cannot be finite set. So as a corollary, you can conclude that there are infinitely many primes. So is the whole thing clear to everyone? Okay. That this was my proof. Thank you everyone.